A refracting telescope is the classic long tube design many people picture first. It works by using a curved glass lens at the front to bend incoming light and bring it to a focus, where an eyepiece or camera magnifies the image. Because the light path is simple and sealed, refractors often give sharp, high-contrast views of the moon, planets, and double stars. Their downside is that large lenses are heavy and expensive to make. A fun fact: some of the most famous early discoveries, including many of Galileo's observations, were made with small refracting telescopes that were far less powerful than a modern beginner scope. A reflecting telescope uses a curved mirror instead of a front lens to collect light. The main mirror at the back of the tube gathers light and reflects it to a focus, often with help from a smaller mirror that redirects the image to the side or back. Mirrors can be made much larger than lenses, so reflectors became the standard for serious astronomy. They are especially good for faint galaxies, nebulae, and star clusters. An interesting fact is that the largest visible light telescopes on Earth all use mirrors, not lenses, because giant lenses would sag under their own weight and distort the view. A catadioptric telescope combines lenses and mirrors in one compact design. A curved front corrector plate helps shape the light, while mirrors fold the light path back and forth inside the tube, giving a long, effective focal length without a very long body. This makes these telescopes popular for people who want one instrument that can handle planets, the moon, and many deep sky objects. They are versatile and portable, though they can take time to cool to outdoor temperatures. A neat, real-world fact: many backyard astrophotographers use catadioptric designs because they pack a lot of power into a manageable size. The Galilean Telescope is one of the simplest telescope designs ever built. It uses a convex front lens to gather light and a concave eyepiece lens to magnify the image. Unlike many later telescopes, it produces an upright image, which made it useful for early viewing on land as well as in the sky. The trade-off is a very narrow field of view and low magnification compared with modern designs. Its historical importance is huge. Galileo used this basic type to study the moon's craters, the phases of Venus, and the 4 largest moons of Jupiter, helping change humanity's view of the universe. The Keplerian Telescope improved on the earlier Galilean design by using 2 convex lenses instead of 1 convex and 1 concave lens. This setup creates an inverted image, but it allows a wider field of view and greater magnification, which made it far more useful for astronomy. Light enters through the objective lens, comes to a focus, and is then magnified by the eyepiece. Many later refracting telescopes follow this basic idea. A surprising fact is that although the upside-down image seems inconvenient, for astronomy it usually does not matter, because there is no up or down in space. An achromatic refractor is a refracting telescope designed to reduce color fringing, the rainbow-like blur that simple lenses can create. It does this by combining 2 kinds of glass in the front lens so different colors of light come closer to the same focus. That gives a cleaner image, especially around bright objects like the moon and planets. Achromatic refractors became a major step forward because they made larger and more practical refracting telescopes possible. An interesting fact: before this improvement, bright stars and planets could show distracting colored halos, which limited how clearly early astronomers could study them. An apochromatic refractor, often called an APO, is a more advanced refractor built to control color even better than an achromat. It uses special glass and carefully designed lens groups to bring several colors of light to nearly the same focus. The result is a very sharp, high-contrast image with little false color, which makes APOs prized for both visual observing and astrophotography. They are usually more expensive because the optics are harder to make well. A fun fact: some of the smallest premium telescopes people carry to dark skies are APO refractors, yet they can produce stunning images of nebulae and galaxies. The Newtonian Reflector is one of the most popular telescope designs in the world. It uses a curved primary mirror at the bottom of the tube to gather light. Then a small flat secondary mirror near the top sends the focused light out to an eyepiece on the side. This design is simple, affordable, and excellent for seeing faint deep sky objects, because a large mirror can collect lots of light without extreme cost. It does require occasional alignment, called collimation. A cool fact: Isaac Newton built the first successful version in 1668 to avoid the color problems that troubled early refracting telescopes. A Dobsonian is really a Newtonian reflector placed on a simple, low-cost mount that moves up, down, and side to side by hand. The genius of the design is that it puts most of the budget into a large mirror rather than an expensive tripod or tracking system. That means beginners can get a lot of light-gathering power for the money, making Dobsonians fantastic for viewing galaxies, nebulae, and star clusters. They are often bulky, but easy to use. A surprising fact, the Dobsonian design helped bring truly large amateur telescopes into backyards, with some hobbyists building versions big enough to climb a ladder to use. A Cassegrain telescope is a reflecting design that folds light into a compact shape. Light enters the front, reflects off a large primary mirror at the back, then bounces from a smaller secondary mirror near the front and passes through a hole in the primary to reach the eyepiece or camera. This folded path creates a long focal length in a short tube, making the design useful when you want high magnification without a huge instrument. Many modern telescopes are based on Cassegrain ideas. An interesting fact, professional observatories often place instruments behind the primary mirror, exactly where the light exits in this design. The Ritchey-Chrétien Telescope is a specialized form of Cassegrain reflector, designed to produce sharp images across a wider field. It uses two carefully shaped hyperbolic mirrors that reduce certain image distortions, making it especially useful for research and astrophotography. Because it can deliver crisp stars over large camera sensors, this design is common in major observatories. It is more complex and expensive than a basic reflector, but the image quality can be excellent. A famous fact, the Hubble Space Telescope is a Ritchey-Chrétien, which shows how important this design is for capturing detailed pictures of distant galaxies and nebulae. A Schmidt-Cassegrain Telescope, often shortened to SCT, is one of the most common all-purpose telescopes sold today. It combines a thin corrector plate at the front with mirrors inside that fold the light path, giving a compact tube with a long focal length. That makes it good for the moon, planets, double stars, and many deep sky targets, while still being portable enough for many hobbyists. SCTs are often paired with computerized mounts for easy object finding. A neat fact, because they pack so much focal length into a short body, many people can carry an SCT in one trip that would otherwise need a much longer telescope. A Maksutov-Cassegrain Telescope is another compact design that uses a thick, curved corrector lens at the front and mirrors inside to fold the light path. It is known for sharp optics, sturdy alignment, and strong performance on the moon and planets. The thick front lens helps correct image errors, but it can also make the telescope heavier and slower to cool than some other compact designs. Many people like Maksutovs because they are easy to transport and often need little adjustment. An interesting real-world fact, small Maksutovs are popular as travel telescopes, fitting into surprisingly small cases while still offering serious magnification. A Schmidt Camera is a wide-field telescope designed mainly for photography rather than visual observing. It uses a spherical mirror and a special corrector plate at the front to reduce image distortion over a broad patch of sky. Instead of focusing on a flat plane like many telescopes, classic Schmidt cameras focus on a curved surface, which originally worked well with curved photographic film holders. These instruments were excellent for sky surveys, capturing huge numbers of stars and galaxies in a single image. A remarkable fact, some of the most important maps of the night sky in the 20th century were made with Schmidt cameras. A solar telescope is built specifically to observe the sun safely and in detail. Some use special filters to block most of the sun's intense light, while others are designed to isolate a very narrow color of light that reveals features like prominences and surface texture. Because the sun is so bright, never use an ordinary telescope to look at it without proper equipment. Solar telescopes let people watch our nearest star as an active, changing world rather than a plain bright disk. A fascinating fact, with the right solar setup, you can sometimes see eruptions on the sun that are larger than Earth. A radio telescope does not collect visible light at all. Instead, it detects radio waves coming from space using a large dish antenna or other specialized receiver. The dish reflects those waves to a sensor, which turns them into data that computers can analyze. Radio telescopes can study cold gas clouds, pulsars, black holes, and galaxies that may be hidden from ordinary optical telescopes by dust. They also work day and night, and through clouds more easily than visible light telescopes. A striking fact: some radio telescopes have detected signals from pulsars, objects so extreme that they spin many times each second and beam radio pulses like cosmic lighthouses. A microwave telescope observes a shorter wavelength part of the radio spectrum, often using highly sensitive detectors cooled to very low temperatures. These instruments measure faint microwave radiation from space, including the afterglow of the early universe called the cosmic microwave background. Instead of making pretty eyepiece views, they create maps of tiny temperature differences that reveal how matter was spread out long ago. This helps scientists understand how galaxies later formed. An amazing fact: by studying microwaves, astronomers can look back to a time when the universe was only about 380,000 years old, far earlier than ordinary telescopes can directly see. An infrared telescope detects heat-like radiation that lies just beyond red light. This lets astronomers see objects that may be cool, dusty, or hidden behind clouds of gas and dust that block visible light. Infrared telescopes often need special cooling because the telescope itself can glow in infrared and interfere with the signal. They are excellent for studying newborn stars, planets around other stars, and the centers of galaxies. A surprising fact: some of the most dramatic space images come from infrared observations, where dark, dusty regions in visible light suddenly become transparent and reveal stars forming inside. A visible light telescope is any telescope designed to observe the same range of light human eyes can detect. This includes most classic backyard telescopes and many major observatory instruments. Whether it uses lenses, mirrors, or both, its job is to collect more visible light than your eye can and bring it into focus for viewing or imaging. Visible light telescopes are ideal for the moon, planets, stars, galaxies, and nebulae, especially from dark locations. An interesting fact: even though this is the kind of light we know best, visible light is only a tiny slice of the full electromagnetic spectrum astronomers use. An ultraviolet telescope observes light beyond violet at wavelengths that are mostly blocked by Earth's atmosphere. Because of that, ultraviolet astronomy is usually done from high-altitude rockets, balloons, or spacecraft. Ultraviolet light reveals very hot and energetic objects, such as young massive stars, hot gas, and material swirling around compact objects. The optics and detectors must be specially designed because ordinary materials do not always handle ultraviolet light well. A cool fact: by looking at ultraviolet, astronomers can trace regions of intense star formation that may appear much less dramatic in visible light. An X-ray telescope studies some of the most violent places in the universe. X-rays come from extremely hot gas and high-energy events, such as matter falling into black holes, exploding stars, and the hot gas between galaxies and clusters. Because X-rays would pass straight into or through a normal mirror, these telescopes use mirrors set at very shallow angles so the rays glance off rather than crash directly in. X-ray telescopes must usually be placed above Earth's atmosphere in space. A fascinating fact: many black holes are found not by seeing the black hole itself, but by detecting the bright X-rays from nearby matter heating up. A gamma-ray telescope detects the highest energy light known, produced by some of the universe's most extreme events. Gamma rays can come from exploding stars, active galaxies, pulsars, and powerful bursts that briefly outshine almost everything else in the sky. Since gamma rays are too energetic for ordinary focusing mirrors, many gamma-ray telescopes track how the rays interact with detectors or with Earth's atmosphere. Scientists then reconstruct where the radiation came from. An astonishing fact: gamma-ray bursts can release in seconds as much energy as the sun will emit over its entire lifetime, making them among the most powerful events ever observed. A space telescope is any telescope placed above Earth's atmosphere, usually in orbit, or farther out in space. Getting above the air avoids blurring from turbulence, removes weather problems, and opens parts of the spectrum, like ultraviolet and much of infrared, that the atmosphere blocks. Space telescopes can be built for visible light, infrared, X-rays, and more. They are expensive and hard to repair, but the scientific payoff can be enormous. A memorable fact: images from space telescopes have not only advanced research, they have also become some of the most widely recognized and inspiring pictures ever taken. A ground-based telescope is any telescope operated from Earth's surface, from a small backyard setup to giant observatories on mountaintops. These telescopes are easier to build, upgrade, and repair than space telescopes, and they can be made extremely large. The atmosphere does blur visible images and block some wavelengths, but astronomers fight back by choosing dry, dark, high locations and using advanced technology to sharpen the view. Ground-based telescopes remain the workhorses of astronomy. A surprising fact: some of the biggest optical telescopes on Earth use mirrors many meters across, far larger than anything practical to launch into space. An interferometer links two or more telescopes, so they work together like one much larger instrument. By combining the incoming waves very precisely, astronomers can achieve much finer detail than a single telescope of the same size could provide. Interferometers are especially powerful in radio astronomy, but versions also exist for infrared and visible light. They do not always collect as much total light as one giant mirror, but they can reveal incredibly small structures. A striking fact: radio interferometer networks spread across continents can produce sharpness so high that they have helped image the shadow of a black hole.